Welcome everybody. Welcome at this live session about superalloys machinability. A subject that is a bit interesting in that sense that, and I put some things out on social media about the latest insights in machinability of century-old alloys, and some people reacted. They said, "Wait a second, superalloys are not century-old." As a development. Well, it all depends on how you define it, of course, but I would like to remind you that some people claim that superalloys are kind of a further development of stainless steels. And if we talk about stainless steels, perhaps some of you know that the oldest physical proof, it's a big pillar in Delphi in India, the oldest proof is from around 400 AD, and the pillar is made out of corrosion or rust-resistant steel. So, with some creativity and imagination, one could say that superalloys indeed are very old. Now, superalloys are used today in quite a lot of industries, especially in applications where high performance is needed. And later on in the presentation, we'll define high performance, but it's typical, a material used in aerospace, in power generation, that type of applications. And superalloys have quite a lot of advantages, but there are also some disadvantages. One disadvantage is they are rather expensive, which is something we should remember later on when we start to look into machining, because losing a workpiece when the material is a superalloy is quite an expensive exercise. So reliability in machining is rather important. The other thing is that actually machining of superalloys, when I compare it with the more traditional steel alloys, is challenging. It's difficult. It's different. And that's why we have this presentation, to dive into what exactly is now machining of superalloys, and where are the real challenges, and more important, how can we cope with them, how can we handle it. My name is Patrick de Vos. I'm your host of today, and I have a model, kind of, one could say, a model of a machining process, which I want to share, because this is the framework on which I base a lot of statements I make. I try to define machining as a physical process. Machining is a process where a tool is removing material through a process of deformation and shearing off. Now, such a process, there's lots of phenomena taking place: mechanical, thermal, chemical, whatever. It's a rather complex system, and machinability is about the ability to bring balance in this system, where I have a cutting tool which is confronted with a workpiece material, and I want balance. I want the loads acting on the tool and the load bearing capacity of the tool be in balance. And then I have a balanced machining process, and the variables in this, one could say equation, they are numerous. There are quite a lot of variables we have to take into account if we want to understand this physical process. And creating a good machining process is solving the equation, one could say. And to be able to solve this equation, quite a lot of knowledge domains, skill domains are needed. One could say the profession of a machinist is a rather difficult one. One has to have insights in physical phenomena, one have to understand organizational stuff, and so on and so forth. And solving the equation also means that we have to be able to measure. We need metrics, and the very typical metrics we have in machining are the use tools. And if I go back later on to machining of superalloys, you'll hear me talk quite a lot about wear processes and deterioration stuff and so on. The quality of the finished workpieces is another metric. Don't underestimate still today the opinion of the operator, especially when it's a skilled operator. He can read the process, and listening to what he saw or observed is a very important metric. And in the end, of course, one could say machining, it's a technological thing, but it also is a commercial thing, because with machining we want to produce workpieces for customers, and in the end it's the customer who decides if we did a good job. And a good job in machining can be multiple things. It can relate to costs, it can relate to productivity, it can relate to promises which were made on delivery time, it can relate to sustainability stuff, and so on and so forth. So this is kind of the model I use. And in the background, this model I want to use when we talk about machinability elements of superalloys also. If you want to learn more about this model, there's quite a lot of literature available. And if you are interested in this, just give us a message, and we will inform you more about it. As always, I'm not alone here. I'm together with two colleagues, two friends of mine that do the technology behind this type of event, that it can work as it's supposed to work. What we are going to talk about, there are three big things. The first part is, what one could say, it's a bit of metallurgy. What exactly is a superalloy, and what are the elements in a superalloy that relates to the machinability, and how do we handle those things? The second part is hands-on practical advice. Do this, don't do this, don't do that. And the third part is a bit special perhaps, but I want to make a comparison with titanium materials, because so often people say, machining a superalloy or machining a titanium alloy is basically the same stuff, Now, it's not. Saying that machining titanium alloys is as machining superalloys, it's like saying that machining steel or machining cast iron is the same thing. But it's not. There are differences, and I want to draw your attention to those differences, just to make clear that because it's two rather expensive materials, a titanium alloy and a superalloy are expensive, and if we make false suppositions, if we think, we suppose, it could lead to that we lose workpieces. And as I already said, it's a bit of a dangerous exercise. Now, superalloys, the name superalloys, perhaps interesting to know. The name superalloy, or the word superalloy, was used for the first time in a report made in a metallurgy lab in Boeing in 1954. And one of the people there was referring to what was a nickel-based alloy, that this is a superalloy, as it seems it behaves completely different from other materials we work with. A superalloy keeps its strength at very high temperatures, instead of losing it like we normally see in metals. And that is the origin of the word superalloy. Superalloys, the reason they keep their strength at very high temperatures is the so-called prime gamma precipitation strengthening. I'm going to come back to it because it's a phenomenon we machining people have to be aware of. Now, superalloys, as I already said, it's high performance materials. They are developed, designed to be used in circumstances where the working temperature in which the materials are used is beyond 600-700 degrees Celsius. Now, if you look to that kind of a definition, it becomes obvious that the industry segment where superalloys were initially, or the modern superalloys were initially developed in, was aerospace, jet engines, where we have parts where the working temperature is very high, and where we needed, or people needed, materials different from the traditional materials. If we talk about superalloys later on, we have to be a little bit careful, because the superalloy is a family name, and there are quite a lot of members in this family, so we have to be a bit careful there. Well, we find mainly these materials back, as I already said, and they originate from aerospace. There we very typical find nickel-based materials, Inconel 718 is kind of the type material for aerospace applications. We also find power generation. There it's more the cobalt-based superalloys we will meet. And also there are applications in the medical segment, where it's the more complex alloys. Cobalt, chromium, molybdenum are typical examples of materials we use there. Superalloys, as I already said, quite a lot of members, but we can split them in three groups or subfamilies. You have the nickel-based superalloys, mainly found, as I already said, in aerospace applications. Cobalt-based superalloys, where the main material is cobalt. And then we also have the iron-based superalloys. The iron-based are kind of the oldest superalloys. I would say iron-based is mainly there where we look for less expensive materials. It's perhaps dangerous what I'm saying now, but from a performance perspective, iron-based are the least ones, but on the other hand, they are also the cheapest ones. But these are the three big families. What we have in superalloys is that quite a lot of the materials we are confronted with are commercial indicated or have commercial indicated names. That means that contrary to steel applications or cast iron, where there are standards and norms, it's a bit of a thing we still miss in superalloys. But I'm going to come back to it because people working with standards and norms are working on that. Now, the key properties we use superalloys for is the high strength of the materials, and especially high strength, which is kept at high temperatures also. Resistance to thermal fatigue. If the materials are exposed to quickly changing temperatures, the materials can handle that. A traditional steel, when you expose it to quickly changing temperatures, there will be temperature cracks appearing in the structure. Superalloys are more resistant to that, and it's corrosion resistance. Especially certain types of superalloys show rather high corrosion resistance. Now, superalloys, and I take here the example of a jet engine, you find very often in a construction together with, I call it here, sister materials. If you look in a jet engine, you find titanium alloys, superalloys, some parts perhaps in steel, some parts in aluminium, some parts in stainless steel. You find all these materials kind of always in the same assembly. And that's why also machining people, they always think, it's a group of materials. Now we have to be careful with that, because if I take titanium alloys and superalloys, and I take here two very typical representatives of those materials, it's titanium 6Al4V, which it's commercially perhaps the most used titanium alloy, and I compare it with the superalloy Inconel 718, or perhaps for the first time in this presentation I talk about alloy 718. I'm going to explain within a few minutes what that is. And if I compare these two materials, what we see is that from a strength perspective, at lower temperatures, titanium is stronger than a superalloy, than Inconel 718. However, when temperatures go above 400-500 degrees Celsius, titanium starts to lose its strength, while Inconel 718, alloy 718, keeps the strength. And keeps that strength up to close to 1000 degrees Celsius, where titanium by then already lost nearly all of its strength. That's a big difference. The other big difference between the two materials is the density. What you see is that titanium has a low density, whereas superalloy has a high density, even perhaps higher than traditional steel. The machinability, when already here as a general picture, but later on, of course, we go much more in detail. I would say if you compare the two, machinability of a superalloy is lower than the machinability of titanium. Uh, but I specify that more in detail later on. Now, alloy 718, I already used the word a couple of times. One of the original superalloys, and still today quite a lot used, is that so-called Inconel 718. Inconel 718 is a commercial name of a material which basically contains around 53% nickel, with a lot of properties related to that. Now, a group of people sat together and they said, we always compare superalloys with steel materials and try to define machinability of superalloys compared to machinability of steel alloys. But that is a bit of a handicapped comparison, because we try to compare the two different type of materials, and that is not always working well. So we kind of need a standard when we talk about superalloys. We need a reference material, and that material became what is referred to today as alloy 718. If a material is allowed to be labeled alloy 718, and the origin of it is Inconel 718, it has a number of standardized norms, properties, features about composition, about properties, about also, from our perspective, machining people, machinability elements. Alloy 718 shortly is the reference material we use more and more when we talk about machinability of superalloys. Now, just that you have an idea, alloy 718, what is alloy 718? It's a rather hard material, and depending on how it is produced and thermal treatments and so on, it's between 30 and 45 Hartford Rockwell C. It's a rather tough material at the same time. That's one of those things, that makes superalloys super. They can be hard and tough at the same time. There is serious strain hardening in this material when you deform it, which is a wanted property, I would say, from a constructive perspective, there where we use superalloys as construction materials. For us machining people, however, this is something to worry about. And very often, if we talk about superalloys, we will take the machining practices for Inconel 718 or alloy 718, I should say, as a reference, and we compare with, we call that a bit, it's the wrong word, but anyway, the standard approach. And compared to that, we will classify other superalloys in terms of how to select cutting tools, how to select cutting conditions, and so on. With other words, in short, alloy 718 is a bit of a reference material when we discuss machinability of that big family superalloys. Now, if we talk about material properties and if we talk about machinability, machinability being kind of a very vaguely defined thing that says to which extent is it easy or more difficult to machine a material. Now, it is as vague as that. I always, since years, have people discussing, what is the machinability of a material, and they want to hear percentages. Now, don't talk about percentages, because machinability as such is not defined. There is no unit to it. It's a very vague thing, and if we want to talk, we have to be more concrete and pick out one specific thing in the machining world, a cutting condition or a type of tool or a productivity rating or a cost efficiency rating, and take that as reference, and then we can talk concretely. But as such, machinability is very vaguely defined, and machinability is what ISO, since 50, 60 years now, tries to capture in that so-called ISO system. Where we talk about P materials and M materials and so on. What we should not forget is that this system originally was established somewhere in the mid-70s of the previous century. an age where materials were steels and cast irons, and all the other materials we have today and we have to machine were nearly not existing. That means that the original ISO approach is based on mechanical properties only. Hardness, toughness, ductility, that type of things. And if we look to the materials we are confronted with today, that is just not enough. That's why people have been looking to find better approaches and a system I personally like a lot, because from a theoretical perspective, it explains quite a lot of phenomena we are confronted with. And from a practical perspective, it gives us quite a number of really working handles to figure out machining strategies, to figure out tool selections, cutting data, all that type of thing. When we have to machine materials, not only steels and cast irons, but also the other materials we see today, the non-ferrous materials, the superalloys, the titanium materials, and so on. And this system is based on basically 5 properties. You have the hardness, the abrasiveness, and the ductility, the adhesiveness. Kind of, that is the similar part with the ISO approach. But added to that are 2 other variables. One variable is strain hardening effects. To which extent is a material going to show strain hardening when being deformed? And let's not forget, machining is a deformation process. So if you have serious strain hardening in a material and you machine it, automatically you create strain hardening zones in the material, and that has consequences. And the other thing is thermal conductivity. As you deform material, heat is generated, and that heat needs to be evacuated. And if the heat is not so well evacuated, that has consequences for the machining process. And now, think on superalloys, think on titanium alloys. They have low thermal conductivity. They do not take out the heat out of the cutting zone and evacuate through the chips or in the workpiece. That means that property we need to take into account also if we want to evaluate machinability in certain materials. The most beautiful thing, I think, in this system is that we can finally jump out of toolware insights, which were more than 100 years old, and based on it, where we said flank wear, crater wear, that's what you need to have on a cutting edge, and all the other wear patterns should be avoided. Now, that is very correct, perhaps, if you talk about traditional steel materials, but if you talk about the materials we are confronted with today, think on superalloys, titanium alloys, that becomes completely irrelevant. Because in those materials, you will see other wear patterns become predominant. And I don't say it makes us happy, but we will have to accept it. And to which extent a certain property is present in a certain workpiece material, we can link to that very typical wear patterns. Much more accurate than the before flank and wear. Here we can accept in a number of cases plastic deformation. We can accept in a number of cases notch wear. We can accept, and I say it doesn't make us happy, but we should accept it because it's a reality of the machining life. We build up edge perhaps. And again, it doesn't make us happy, but it's a reality. And I'm going to come back to it because, superalloys are put together with titanium alloys in the so-called ISO S group, and that's it. I'm not going to spend more time on it, that ISO system and why it doesn't work fully. Let me jump directly to that system with the 5 axes, the 5 variables, the system which is developed on the guidance of Professor Stahl in Sweden. If you look to these 5 properties, and what you see here in the picture, the blue line somewhere around the center represents traditional steel. And if I say steel is for me an average material, more important, steel is a material we know very well because we machine it since 150 years. So we kind of know how the material behaves, and we kind of know what is a good cutting tool and what are good cutting conditions for that material. And if I compare with that classic material, and I put here titanium as a material. The green part represents titanium, the 5 properties of titanium. The yellow part represents a superalloy, and I take here alloy 718 as the reference. What we see then is that compared to steel, hardness, abrasiveness, ductility, adhesiveness are all to a bigger extent present in a superalloy than in traditional steel materials. If you look to the green part, titanium is less demanding there. If you look, on the other hand, to strain hardening and low thermal conductivity, a low ability to evacuate heat away, we see very big differences. So whatever, if we have to machine a superalloy or a titanium alloy, it's strain hardening we will have to cope with much more than what we are used to when we machine steel, and low thermal conductivity. But if you look to the yellow and the green part, you see differences. Titanium or a titanium alloy is not the same as a superalloy. There are differences. Also, very careful, much more than in steel. If we talk about superalloys, it's not only the material itself, but it's also the form or the shape under which the material is delivered to be machined. Is it a casting? Is it forged or whatever? Because those things will, in some cases, seriously modify machinability. So when we machine superalloys, it's about to realize they are different from steel, more demanding towards a cutting tool. They are also different from titanium alloys. Don't put it on one pile. It's 2 different things. And much more also the form under which the workpiece you have to machine is presented is also a very important element to know. Now, if you know your material, if you know to which extent certain properties are available, are present in the material, that helps you a lot to select cutting tools. What you see here is a schematic overview from depending on which properties are there in the workpiece materials, what is the guidelines we could give you when you have to select cutting tools. It's very generic here. Huh? It's not about use this brand and use this carbide. No, it's much more generic. It's about tougher or harder or more positive or stronger or whatever. It's very generic guidelines. And the same we can do when it's about cutting data, machining data, how to select your machining data, how to select cooling, no cooling, how to select cutting speeds, feeds, depths of cut, and so on. And I remind you, that's why I put it in this figure also, because here you solve kind of the machining equation. You know your material, you know the properties, that guides you to select a tool, that guides you to select machining data, cutting data, and then you start machining and you ask yourself the question, did I do a good job? Did I solve the equation well? Well, the used tools will tell you. Because whatever, if a certain property is the predominant property you want to tackle, let's say it's strain hardening, like we have in superalloys. Strain hardening means that your tools needs to be selected first based on the geometry. We need sharp geometries. The carbide grades have to support that sharp geometry. And the cutting conditions, you should use lower cutting speeds and higher feeds and depths of cut be a bit careful with. And you do all of that and you start machining and then you are, is this now the best? Did I do well? Well, if you see wear patterns, plastic deformation and so on, that are typical for that property, that means at least the operation is working according to expectations. It could be that the wear pace is too high. then you need to adapt your choice, increase, reduce certain things, but your basic choice was good. If on the contrary you would see a lot of broken cutting edges, well, that's an indicator, that's an early warning. You did wrong with your solving the equation, because if strain hardening is the issue and you find a lot of broken cutting edges, that is not logical. That combination. A workpiece material. 5 basic properties, an idea about it. You don't need always to have a number necessarily wise. It's very often good enough to have an indication. Will it be more? Will it be less? And on that you can base your tool selection, perhaps even your machining strategy selection, cutting conditions. Where is your indicator that I did well or not? I need to modify. If I translate that now a bit more in concrete to superalloys, and in this chapter, what I want to do is bring together some insight, academic insights, the theoretical part, kind of, if you want, in what exactly is taking place during machining of a superalloy, and practical things, what people observe in a workshop. If I bring that together, it gives me some basic advice to follow. Some general practices when you have to, and I take again, and I see a big mistake here on the slide. It says alloy 781. It should be 780. Of course, use sharp tools. That is basic advice. That is the primary advice. The cutting should be done with a sharp cutting edge. And there's a number of reasons. The main reason is to minimize heat generation, because superalloys show a rather low thermal conductivity. So if you generate too much heat, there will be too much heat concentrated in the cutting zone, and that has negative consequences. The other thing is that a positive acting cutting edge creates less deformation before it's cutting, and that means that the strain hardening effect will be less present during the operation. Make sure the tool is working because you have a sharp tool in stable conditions. Avoid micro vibrations, with other words, because that's the weak part of a sharp cutting edge. It's sensitive for micro vibrations. It's sensitive for too high cutting forces and too big variance in cutting forces. We have to take care of that. Ship evacuation, because as we work with positive geometries, ships will show a tendency to be long. That means that we have to manage those ships in the best possible way and evacuate them in the best possible way from the cutting zone. Heat generation, that's the thing to worry about. Make sure you do whatever possible to generate as little heat as possible, and the heat which is generated evacuated in the best possible way. With some thicker ships, cooling methods are important here, and so on. Avoid interrupted cut as much as possible. If you think on a milling application, of course, you are confronted with it all the time. But also in milling, you can, through the strategy you select, you can create a situation where the milling becomes less interrupted, by means of speaking. I'm thinking of dynamic milling, radial milling, all that type of stuff. Make sure you have the correct cutting conditions. That your cutting speeds are not too high, your feeds are not too low but not too high, your depths of cut should be big but not too big. The window in which you can maneuver talking about cutting conditions is compared to traditional steel rather narrow, and you should bear that in mind. Use climb milling, very typical when you have milling applications. If you have to do threading operations, the pre-drilled hole, if it's an internal thread, is important than the diameter, because you have strain hardening effects in these materials, And the success of the threading operation, the success of, if it's thread turning or tapping or milling, whatever, the success of a threading operation in stainless steel, in superalloys, is very often defined by the pre-drilling operation. Bear that in mind. And make sure you inspect your tools on a regular basis, because the pace with which wear develops in superalloys in general is higher than when we machine traditional steels. Tooling technology. Make sure you use correct tooling. In the past, we didn't have really tools which were designed for superalloys. Today, we have them. Use them. Prioritize geometry in your tool selection. Geometry first, grade second. The geometry should be sharp, and the grade should support a sharp geometry. With other words, a good grade is a micrograin, is a tough grade, and the coating should be of a PVD or MTCVD type. That covers the sharp cutting edge well. But don't overestimate the importance of a coating, because I know people like to discuss coatings, but if your geometry is wrong in a superalloy, if your substrate material is not good, the coating will not really make up for that. Cooling systems are important here. Make sure you spend enough attention to it. Cutting speeds in general are rather low. Feeds should not be too low, but on the other hand, high enough but not too high. Feed selection in a superalloy is a bit of a, sometimes you have to try a bit to find it out. Keep your eyes on tool wear. I'm going to come back to it. Limit engagement time, especially in situations where you do not really cut, but you rub material. So too small feeds, too small depths of cut. Threading, again, is a very dangerous operation here. And there, where possible, modify your cutting conditions in a dynamic way. Depending on where you are during the operation, perhaps you should modify your cutting condition. A milling cutter in a corner should be used with other cutting conditions than a milling cutter along a wall. What we see towards the future talking about these materials is that we see more and more specifically developed tools for superalloy applications. Keep your eyes on that. Superalloy machining is an application where people still have their eyes on cutting speeds, because by definition they are low. And every improvement in cutting speeds, increasing cutting speeds, would lead to higher productivity and better surface finishes. So it's under the attention of people, and obviously, superalloys, as they are so critical, deserve the best possible machine tools when you have to machine the workpieces. Cryogenic machining seems to have high potential for superalloy machining. Of course, it demands specific installations, safety things, and so on. Laser assistant machining. Lots of universities are doing experiments with combining typical machining with laser preheating, is a development. And then there is, people look into electrochemical machining as an alternative for typical machining, because electrochemical, you do not create machining stresses in the surface, and that, from a quality perspective of a finished workpiece, can be advantageous. Predicted developments, of course, smart machining, Internet of Things, because I already said, if possible, modify cutting conditions during the operation where appropriate, but that's easily said than done. Internet of Things can help us with that. Artificial intelligence algorithms could help us in achieving that objective we have. And then there is, of course, the interaction between additive machining and subtractive machining, where some parts can move from one to the other, and where a combination of the two could lead to big improvements. Now, tool deterioration, when you have to machine superalloys, if you machine a superalloy, what you see is that basically you find all the wear patterns we know. But the two that normally will be the primary one are notch wear and plastic deformation. Notch wear due to the strain hardened surfaces of workpieces, and plastic deformation due to the lower thermal conductivity in these materials, which means that more heat will stay in the cutting zone and perhaps overheat the cutting edge, the cutting points. But also the other wear patterns we will see. And again, careful here because I use superalloys, but yeah, that's what the diagram tries to show you, how different types of superalloys lead to more or less predominance of certain wear patterns. Why do we have? This is the traditional thing. The strain hardening gives you the notch wear. The low thermal conductivity gives you the plastic deformation. But you have also the adhesiveness leading to build-up edges and things related to that. You have rather high cutting forces, could lead to cracks, could lead to shipping, could lead perhaps to breakage also. How do we act here? What is important to counteract if something goes out of control? That cutting conditions are in line with what they should be for the properties present in the workpiece materials. Cutting conditions should also be in line with the type of tool we normally use, sharp cutting edges, coated cutting edges. Cooling plays an important role here. To which extent is the cooling going to interact actively with the process? Toolpath strategies, milling strategies is an important thing here. To which extent I'm going to expose a cutting edge during the operation to really unfavorable conditions or not. And as I said, even if you are fully under control, you will see that the pace with which the tool wear patterns develop is kind of higher than what we are used of when we talk about steel applications. So keep your eyes on the cutting edge. Important is because the previous things are reactions. If you see, you do. I think to have higher predictability in the process, to avoid destroyed workpieces, which is rather expensive. The material is expensive. You should stay ahead of the wear. You should be knowing what is going to happen and that you know what to keep your eyes on. So the predictability is important, and that's why the machinability system with the 5 properties is so interesting. Heat generation, heat evacuation are important things here. Give it the necessary attention from the beginning. Make sure the process is as stable as possible. The machine tool has stability. The cutting tool has a stability. The two together has the highest possible stability. And if not present, be aware of the consequences. And your tool changes, plan them strategically. Don't wait till it's too late. If we talk about superalloys and tool wear, tool deterioration, it's not about having a tool life which is as long as possible, which we are all used of doing, but it's more about making sure you have full predictability, you are fully under control of the process, so you don't lose workpieces, because that's very expensive. The last part, titanium alloys, superalloys. I know in the ISO system they are in the same group, the ISO S system. However, they are different. And titanium alloys, and at the previous occasion we have been talking about titanium alloys already. If you want to learn more, you should review one of the previous sessions we had. But titanium alloys, mainly titanium. Superalloys, mainly nickel or cobalt or both. That is what we are confronted with. Superalloys, we give you the properties and the consequences of those. If you look to titanium alloys, superalloys have high strength at elevated temperatures. Titanium is also called high strength, but it's a different high strength. It's a high strength to weight ratio. And when the temperatures stay below 400, 450 degrees Celsius, titanium kind of has a higher strength than a superalloy. But when the working temperature where the workpiece you produce is going to be used in is higher, then it's a different story. Superalloys have low thermal conductivity. Titanium has an even lower thermal conductivity. So all the things about heat control, heat generation, heat evacuation, it's important in superalloys, but it's even more important in titanium alloys. Superalloys have a high tendency for strain hardening. Titanium alloys, not so much. That's important. However, titanium alloys show a tendency to chemically react with cutting materials. So here we see differences. Superalloys are abrasive. The strain-hardened spots, the precipitation-hardened spots are creating abrasive effects, where we don't find that so much in titanium alloy, but titanium alloys have an elastic recovery type of thing. They bend easily, and yeah, we have to be aware of that. When we talk about tool selection, superalloys, we listed the things about tool selection. Titanium is different. Cutting edges in superalloys, they have to have abrasion resistance, notch wear resistance, crater wear resistance. That is important. Where in titanium, it's more about the chemical reaction stuff, the build-up edge thing and so on that we have to be aware of. Superalloys, titanium alloys bear in common its low cutting speeds. Titanium alloys, it's even lower cutting speeds due to the lower thermal conductivity. Feeds, superalloys, moderate feeds, not too small, not too high. In titanium, normally we can use higher feeds. It's not going to give mechanical problems when we use very high feeds. In superalloys, you have to be more careful with that. Depths of cut in titanium, take them as big as possible without deforming the workpiece and that type of stuff. In superalloys, you have to be a bit more careful again, because if you go for bigger depths of cut, you are going to generate more heat, which is part of the game then, and yeah, that you have to handle that. Superalloys high pressure cooling systems are interesting. Titanium, it's more about lubrication. That is what we have to be careful about. Superalloys, I would say it's the more conservative machining strategies with the lower speeds, higher feeds that we go for, while in titanium alloys, it's there we can use, or we are closer to the more typical high-speed machining systems. It's not the high speed like we know in steel and so on, but it goes that direction. So superalloy, when you talk about machinability, machining strategy stuff, I would say it's very vague now, but I would say go for high feed approaches, where titanium alloys, high speed, high feed methods are, or machining strategies are a better approach. Tool deterioration. Cutting edges when being used in titanium or in superalloys look different. Dominant wear in superalloys is notch wear and plastic deformation, but you will see all the other wear patterns also appearing, where in titanium alloys you see more plastic deformation and build-up edge wear in general. That is what we notice there. If I try to put it in a table, superalloys, and between brackets again, it's alloy 718. Titanium alloys, you see here the differences. Thermal conductivity, cutting forces is important. Heat generation is important, and those kind of things steer how we do machining, how we select tools, and how we select cutting conditions. Both in ISO S, yet when it comes to a machining strategy, a tool selection, cutting data selection, there are differences we have to be aware of. Don't just copy paste between the materials. That's basically the message I want to bring you. It's both materials where cost efficiency, productivity, delivery time, production time are still challenging. If I compare with the more traditional materials, it's more expensive to machine those materials. Productivity is lower. Production times are longer. Predictability, controllability are lower. So innovation is very important to overcome these challenges. And if this is for you the daily thing, that type of materials, you should keep your eyes on developments of tools, of machine tools, of insights on whatever. The challenges when you machine these materials are different from tradition. And tradition, I mean with that steel machining, cast iron machining. Understanding the differences is key for understanding how to machine these materials. Future trends and strategies, I think that especially the digital side of it should have our interest, because predictability is important, because the workpieces are expensive. But predictability we can only have if we fully can follow what is taking place during the process. And to be able to do that and to react accordingly to what we observe, we need those digital tools which are developed more and more. And as a last thing important, I know the typical machining people, they do not like theory. They say, theory doesn't work anyway. And on the other hand, people in the academic world, they don't fully understand always the practical reality in a workshop. Well, especially in this type of materials, where also metallurgical developments are ongoing, I think it's important that instead of neglecting each other, that people here should work more closer together to fully understand how really interactions are between workpiece property, workpiece material properties, and on the other hand, how we do the machining of these materials, the strategies we use, the tools we use, how we determine cutting conditions, and so on. I hope in a very short time, it's less than an hour, it gives you some insight in superalloy material, the challenges, the differences with other materials, also the differences with titanium alloys. If you want a copy of this presentation, as always, it is of course available. Just send us a message and we will send you a copy of the presentation. If you want more information, more background information, also there you are just one question away from having more information. Before we stop here, let me quickly check, because we have some minutes left, I was going to say if there are some questions, but it seems there are a lot of questions. So let me try to find some questions that could be of general interest. I can't handle all these questions here in the time which is left. I pick out some questions here which I think are rather interesting for everybody. On the other hand, all the other questions, I'll give you an answer later on in the comment function, in the chat function. The first question, most coatings contain titanium. Is it correct to say that tools for working with titanium alloys could also be uncoated? Yeah, could. I think the one who asked the question means should, because that's, of course, cutting edges can be coated when you machine titanium. The question is, and that's an ongoing discussion of metallurgical people since ever, that if you have titanium, and if you have a cutting tool with a titanium coated surface, and if you bring those two together, isn't there going to be a migration from the titanium coating into the workpiece or vice versa? Now, I'm not a metallurgist, let me first say that, but in general, making that statement in just in general, it's cannot is yeah, not good, because what we should not forget is that the titanium we machine is a titanium alloy, and the titanium we use for coatings is not titanium, but is also kind of a chemical connection of titanium with other, it's titanium carbide or titanium carbonate, right? So making that the titanium will migrate from one place to another if you bring them together is sometimes yes, sometimes no. But it's not always. I have seen quite a lot of machining applications in titanium workpieces where coated cutting edges were used with good results. The next question, would you prefer a cutting tab or a forming tab for Inconel 718? For sure a cutting tab. A forming tab, yeah, it both will work, but a forming tab will create such a strong and thick strain-hardened layer that the thread itself will become very brittle, or very relatively brittle and sensitive for quickly wearing out. So it's of course depending on the application of the thread on the workpiece, but in general I would say I prefer thread cutting, tapping, and not thread forming tabs. Then, yeah, we have some more time left. What kind of wearing mechanism is dominant on a cutting tool during machining of Inconel? Yeah, I talked about it. In normal situations, when it's Inconel, and the cutting tool has been selected as it should be selected, and the cutting conditions are what they are supposed to be, you will see notch wear, and you will see plastic deformation. Or that should be then the predominant wear pattern. The wear patterns on which you base all your thinking about when to replace a cutting tool, when did I reach tool life, and so on. How can one see when a drill is worn so much that it should be discarded or resharpened? That's $1 million question. Because when you talk about wear patterns, first of all, on a drill, yeah, you can't see the drill while functioning because the drill is in the hole. So you have to hope for the best. That means that you have to evaluate the drill before you start using it, if it's still good enough, yeah, to drill the next hole, kind of. Today, I would say that is based a lot of on the expertise of the operator. Very often it's a gut feeling he has. This will work, this will not work, and I replace the drill. This is a very typical domain. I think drilling as a whole is a very typical domain where Internet of Things philosophies, artificial intelligence approaches can help us a lot. I have seen quite a lot of research work on this domain, but from what I know, practical today, still it's you have to count on the operator. I have seen quite interesting things in laboratory situations, but the big question is, can we reproduce that in a normal workshop? And then, yeah, the question could be a bit different. Yeah, one more question. Are big depths of cut a good idea when machining superalloys? No. Now, they shouldn't be too small also, but big depths of cut in superalloys, remember superalloys, they are difficult in every aspect compared to steel. They are more abrasive, they show a tendency to be harder, they have more ductility, abrasiveness, I already said, they have high strain hardening, and so on and so forth. So, in general, during the machining process itself, big depths of cut are a challenge because your cutting forces will be high, risk for micro vibrations is high, there is quite a lot of heat which is generated going to affect the long length of a cutting edge, and so on and so forth. So, in general, I would say no. On the other hand, but that's more a techno-economical consideration. If you can take the surplus material, the overstock material away in one pass, kind of your cutting edge has to cut through a surface hardened or strain hardened layer only once. If you do it in two passes, your cutting edge has to pass twice through a strain hardened layer. So, and that's a bit the dilemma here. The process itself, I would say, be moderate with your depths of cut. Techno-economical, I would say, if you can do it in one pass, it's better than in two passes. And there you will have to find a balance between those two things. Yeah, one last question, because it's, I think, a very straightforward question. Which machining strategy is best when milling in superalloys? Personally, I think high feed has more advantages than disadvantages when I compare it to other strategies. But that's, yeah, again, it's a very general answer. Yeah, it's also depending on the actual application and so. But in general, I would say higher feed approaches in superalloys is better. One element we haven't been talking about yet, and it's perhaps the most important one, I referred to it once, the expertise of the operator. Still today, the situation is, and more in superalloys and titanium alloys than in other materials, you have to count on the operator. You have to count on his skills. You have to count on his or her expertise to observe, to recognize what is observed, and to know what to do. If what is observed is acceptable or not, and if not acceptable, what to do. Insight in the physical process is important. If you would ask me what is the first thing to do when I want to improve my machining of superalloy workpieces, well, I would say check on the knowledge and the skills of your people. And if you think it can be improved, do so. Send them to a training, an education, whatever. That brings me to the end. Again, the questions which I could not answer because I wanted to respect the time, I will answer later on in the comments, in the chat, which is connected to this presentation. If there are other questions, please do not hesitate. Put them there, send me an email, whatever. I'll try to answer them as good as possible. If you want to have more information on superalloy machining or other stuff, or the technical literature which is available, just let me know. You can send a mail to me, you can send a mail to my colleague Alesia. We will make sure you have all the answers we can possibly give you on the questions you have. For me, it remains only to say thank you again to my two colleagues, Margarita and Alesia, for making this possible, because they are the musicians behind all this technology here. I had just the pleasure of talking about something which I'm passionate about, machining. Next month we have another session, very interesting one. How to determine cutting conditions in small batch machining production. Because very traditional machining conditions are very often determined through trial and error. We try, we see, we correct. But what if you don't have that time to try and correct? What if you only have to produce one workpiece in extremis? How to determine cutting conditions then? That's the subject for next time. Thank you very much for being here. Looking forward to meet you at the next presentation, or in the chat somewhere where your questions are, and we can give you our